Good morning, everybody. It's really a pleasure to have Professor Douglas Finkbeiner with us. And it's really awesome because I didn't expect too many people to appear in Valentine's Day. That's very awesome news. So I'm going to go through some very nice works that he and his nice group has done recently. The list is a little bit long, so I just want to summarize it quite a bit. So Douglas actually graduated in 1994 from University of Michigan, and he has a dual degree in physics and German literature, but we are very lucky that he selected physics afterward. Then he moved to UC Berkeley physics department as a grad student, and he started working very amazingly on actually different parts of the dust that I'm going to mention. He discovered very important source for dust with his group. While in a PhD, he created a dust map for estimating galactic extinction and also galactic microwave emission. And there are none today that are very much important, foreground for the CMB and isotropy experiment. And they were very important for WMAP. So thanks to him. Then he moved to Princeton University for a postdoc when he actually even discovered more evidence for dust. He actually discovered something that was on that time long suspected as spinning dust emission, but after his amazing work, it's not anymore suspected. It's actually a very established source of the dust today, and for actually CMB foreground. And then he also discovered haze, which is curious and unexpected signal for WMAP that is due to the synchrotron emission from the hard spectrum of electron cosmic rays. So it's not actually, his nice work is not limited to this. He also was contributing in SDSS and also PanStar and also DCAP survey, which is 2,000 square degree survey of galactic plane with DCAP. And very recently, with his group, he also actually discovered Fermi bubbles that he won a prize in 2014, Rossi Prize. But quite interestingly, he wants to talk about something completely different today. So we are very much looking forward to hear what you talk about, please.
Okay, thank you, Razi. Yeah, you might be surprised that I'm not going to talk about a subject of my expertise, but rather a subject of my current interest. Well, let's dive in. As you know, AI is in everyday use. You talk to your phone, it predicts traffic for you, all these kinds of things. I was surprised to learn that robo-readers are used on the GRE to read the essays. Yeah, so they have a human reader and a robo-reader, and when they disagree, then somebody looks into it. But instead of having two humans read each essay, they have a human and an AI. And the AIs do very well at that, apparently. And the FDA has just approved a neural net-based diagnostic for diabetic retinopathy, and there are 12 other things in the pipeline for the FDA to approve this year that use AI to help with medical things. This is increasingly used in physics and astronomy. I really should have filled this whole page with examples, given some of the people in the room, so I will just skip over it because I didn't do anyone justice. Deep neural nets, in particular, have shown a lot of success in classification. So it can say that's a cat. It can even put a box around where the cat is. It can even take the image apart and say there's a dog and a cat and another cat and a rubber ducky. And so that's detection as opposed to segmentation. Segmentation is telling you which pixels of the image contain dog. Okay, so that's a harder task than that. That's a harder task than that, and so on. This is all kind of important because autonomous vehicles are going to be driving around on our streets soon, and they have to be able to interpret a scene rather quickly and say, that's a person at 99% confidence, that one's 97%. That's a backpack on the person, okay? It's got traffic lights and cars and all kinds of things. And you want to be able to do this quickly as you drive. And so this has been possible for a few years. Of course, the devil's in the detail. It doesn't work at night, doesn't work in the snow, doesn't work under all sorts of adverse conditions. It works great when it's sunny and clear and dry. There's this relatively new idea called a cycle GAN. So GAN is generative adversarial network, and then a cycle GAN is one that puts them together and goes in a circle. Well, don't worry about the details, but you can turn a horse into a zebra. That's the amazing thing. And you can even turn a video of a horse into a video of a zebra. And you might say, well, it did something wrong. It made the background more yellow. But the training images of zebras have yellowish backgrounds because they're in dry areas. So the cycle GAN doesn't actually know we're interested in the zebra. It doesn't know anything. It's just trying to make images drawn from the horse distribution preserve as many features as they can of a horse while shifting the domain from horse to zebra. I'm injecting some jargon there. And then it's giving you something from the zebra domain, including background. Okay, so that's kind of amazing.
It looks like his stripes are moving around.
Yeah, the stripes hop around. So this, these are early days. Okay, this was rendered one frame at a time. So one frame doesn't know about the next frame, and each individual frame looks reasonable. But they should be doing this in 3 dimensions, including time, so it's continuous in time. And it's actually even worse. You might notice as the horse turns around, the stripes that are painted on it, you see the head moves through the stripes? Right, it did that wrong. Okay. So we've got a long ways to go, but you can go zebra to horse and horse to zebra. It works both ways. You can take a picture of Yosemite in the summer and make it look like it's winter, or vice versa. So these are in general called domain shifting, and you can just define domains with some set of samples from that domain. And what's really fun is only one set has to be sampled. So I could have labeled. I could have a labeled set of training data for summer, and then just some winter images. And I could tell it, make the summer images look more like the winter images, and it can figure that out. That's kind of amazing. Okay, so that was just some eye candy to get your attention. It would be good to know how these things work. So let's dig in a little bit. So one way to think of this whole image classification business is you have a probability distribution function on the space of all possible images. That's a big space. If you have 500 pixel images, it's about a 1,000,000 dimensional space, because there are 3 colors RGB, right? So it's 3 times the number of pixels. So we don't usually in our field think about PDFs on 1,000,000 dimensional spaces. It sounds kind of preposterous. It sounds like something you could never train in a stable way.
Just a guiding question. So how does real intelligence do it? Like brain, how does it do it?
I wish I knew. We have a lot more synapses in our brain than the computers we're using have transistors. But their clock rate is 10 to the 8 times faster. So, our brain is a very different system than these. But there might be some useful analogies. I don't know. But yeah, somehow it's learnable. We learn what a cat is and why it's different from a dog with relatively few examples. We don't need 1,000,000 examples of cats and dogs. So we can learn that and generalize very quickly. So there must be some way of abstracting the features of an image to a high level relatively easily. So this PDF on the 1,000,000 dimensional space, that sounds impossible, but it's actually not. And it's actually mini PDFs, right? There's the cat PDF. What's the probability this is a cat? What's the probability it's a dog? For any given image, any point in that high dimension space. We specify the PDF with samples. This sounds familiar to people who run Markov chains and specify the PDF of their answer for their scientific question with a bunch of samples from a Markov chain. In this case, the samples are just images. We have 1,000 cats, 1,000 dogs, 1,000 zebras. We throw them at the machinery, and we fit this PDF. So we're actually specifying it with samples, but we're approximating it with some fitting function. And that fitting function is fit with an optimizer. So there's nothing shocking here, right? This is very analogous to what you might do in your research. It's just that the fitting function might have 100 million parameters, and the inputs are in a 1,000,000 dimensional space. So it seems daunting. Here's a rough translation guide as you dig into machine learning, neural net stuff. There are lots of terms. These are very imperfect, yet useful analogies. So when you think of a neural net, you can just think of a very big, complicated, sophisticated fitting function. The training data are samples from a PDF. The loss function, that you use. You're minimizing the loss function when you train this thing. If you have taken an information theory class, you would think of that as a KL divergence or something like that, but just a difference between two distributions. It's the difference between what you have and what you want. Okay, what you want is specified by this, and what you have is parameterized by this. They talk about training with back propagation. That's just applying the chain rule. Okay, there's nothing fancy. You're taking derivatives of how well you're doing the loss function with respect to the parameters in your neural net. And you're just doing some gradient descent in that space. So there's nothing too surprising there. They talk about a softmax output function for the classifiers based on activations. You can just think of a Boltzmann factor based on energy, and we'll come back to that. But there are analogies in physics really to all these things. Just some terminology, and I'm following Ian Goodfellow's deep learning book here. There are disagreements about these sets, but I'm going to say AI is everything. A subset of that is machine learning, a subset of that is representation learning, and a subset of that is deep learning with these deep neural nets. And I'm mostly going to talk about deep neural nets for the rest of the talk, but it's important to remember that AI is a much bigger field than just that. And a lot of what I say about the fragilities of these systems and the problems people run into actually apply to much more than just neural nets. But let's talk about neural nets. You've all seen diagrams like this, and they were probably not very helpful. But the idea is you have some inputs, right? So this might be a 1,000,000 dimension space. We're showing 4, not 1,000,000. And then you have outputs. You might have 1,000 classes that your classifier knows about. We're showing 3. And then you have a bunch of connections between these, and each connection